Welcome to the UGC lecture series. This is the PG Pathashala lecture series on computer science, and we are talking about the paper machine learning. This module we are going to talk about a very important machine learning technique called expectation maximization, which is also called as the EM method of learning or the EM algorithm. So, these are the people responsible for the creation of this module. Now, let us look at the learning objectives of this module. The learning objectives of this module are to understand the concept of expectation maximization or the EM, then to explain this EM algorithm using a simple example, a coin toss example. This example will help you to understand the complete mechanism of EM, and then to understand the use of EM for a more complex problem, the K-means algorithm using Gaussian mixtures. So, initially you are going to take a very simple example and explain it without use of Gaussian, normal probability function only, I mean probability only, but in the second we are going to use a probability distribution function. So, the key words here are expectation, maximization, Gaussian and maximum likelihood. So, before we start off, let us first understand what is this expectation maximization algorithm. So, it was presented in a general way as a concept by Dempster, Lard and Rubin in the year 1977. And it is a EM algorithm, as it is popularly called. It is an iterative estimation algorithm, basically an estimation algorithm that can derive the maximum likelihood estimates in the presence of missing or hidden data. Now, this is the important part of the whole issue, and that is the presence of missing or hidden data. With the incomplete data itself, we are able to find out maximum likelihood estimates. So, we have seen before also probabilistic learning, where we use complete supervised learning, we used independencies and so on. So, this is expectation maximization algorithm is used to calculate the maximum likelihood in the presence of missing or hidden data. So, the classical case in such a scenario is the Gaussian mixture, where we have a set of unknown Gaussian distributions. So, we do not know the parameters of the Gaussian distribution, that is what is the mu and what is the standard deviation, we do not know. So, with that we just assume it is a Gaussian distribution and then we have to estimate the parameter. So, basically we are talking about EM is also called as an estimation algorithm. So, it is basically a many to one mapping. So, if you look at this, X, the capital X is the underlying space and small x is the complete data. This is required for machine learning, and then Y is the observation space and small y is the observations. So, x is observed only by means of y of x, and capital X of y is a subset of x determined by y. So, our job is to find out this y. So, the usage of this is very many. One is filling in missing data in a sample. There is lot of machine learning applications where missing data happens. So, filling in missing data in a sample is an important usage. Estimating parameters of HMMs, hidden Markov models, we have not looked at that yet, we will be looking at it later. So, estimating the parameters of that also we can use expectation maximization, we will be talking about this further. Estimating parameters of finite mixture, so you mix two types of data, how that parameters are used for the mixing. Unsupervised learning of clusters, a simple algorithm which we are going to look at in this module itself. Parameters of mixtures of Gaussian distribution called as emojis. There are very many applications. So, that is why this is an important milestone algorithm that is used in machine learning, especially in the case of unknown or missing or incomplete data. So, how do we start describing this algorithm? So, consider a set of starting parameters. So, you are given a set of incomplete data and you assume that the observed data that you have seen, which is not complete, comes from a specific model. Okay, we assume, we do not know the model, we are just assuming the model. Then use this data and the model, the missing data, you formulate some parameters for the model. So, use this incomplete data to formulate some parameters for the model and use the model again to guess the missing value or data. So, this is called the expectation step. In the next step, you have guessed some missing data now. So, that becomes complete data now. So, those are the data values. From those data values again find the most likely parameters for your model, which is the maximization step. So, the expectation step is to estimate the missing data given some parameters. Using that missing data or the data you have derived, you again find out or re-estimate the parameters of the model. That is the maximization step. You keep doing this till it converges, we will come back to that again. So, repeat these 2 steps until convergence. This we will be stressing again and again. So, the general idea is start by devising a noisy channel. So, any model that predicts the corpus observation via some hidden structure. So, you just assume that. Initially guess the parameters of the model. So, usually you guess, it can even be random. If you take it as random, the time taken for completing the algorithm or convergence will be longer. So, normally you make an educated guess, but random also can work. There is no rule that it will not work. Then the expectation step is use this current parameters that you have just guessed or estimated and the observation given to you, which is some incomplete data, and reconstruct this hidden structure, reconstruct the structure. Then the maximization step is use this hidden structure, that is the observations that you have newly got, and re-estimate the parameters of the model, and you keep on doing this until convergence is reached. So, an example of this is the initial guesses, the unknown parameters could be probabilities if in the case of just probability, or it could be the parameters of your Gaussian distribution in the case of probability distribution, if it is a Gaussian distribution. Then you have the E step or the expectation step, where you guess the unknown hidden structure. Now, just to give you an idea of what this hidden structure is, depending on the application, for example, if you have words, the tags could be the observation, passes, your sentence could be the words, and the passes could be the hidden structure, and so on. And you observe, the observed structure will not directly be the tags, will be the words, and could be ice cream for the weather example. So, you observe the structure, then you use the M step or the maximization steps to again recalculate the probabilities and keep doing this till you reach convergence. Now, of course, in many of the probability issues or algorithms, probabilistic learning algorithms, we have used maximum likelihood estimates. So, here also we are using maximum likelihood estimates. So, the general parameters describe the characteristics of a population. The values are estimated from samples collected from that population. Normally, this is the normal way of doing things. So, what do? This parameters, we are saying that it could be just probability, or it could be conditional probability, or it could be a probability distribution parameters. So, both are it could be both. So, what we do is we get some samples from the population, and based on the samples we find parameters to estimate the characteristics of the population. So, this maximum likelihood estimate is a parameter estimate that is most consistent with the sample data. So, it maximizes the likelihood function. We have looked at how we find the probability and conditional probability, which probability is right and what is it. So, the basic setting in EM is X is a set of data points or the observed data. Then you have theta, which is a parameter vector for the model. Okay. Then EM is a method to find the proper model, the maximum likelihood of that particular model parameters, where the theta ML is the argument max of theta for that particular model. So, what we are trying to do is we are trying to maximize the parameters of the model. So, we are learning the model, in other words. So, given the model, we are trying to find the maximum probability of X or the data that generated that model. So, can you understand what we are trying to say? Normally what we do is we take the data and generate the model. Here we are guessing at the model, then we are using that model to guess some data and keep on doing this till you get the proper parameters of the model. So, we are learning the model, in other words. So, calculating that probability of the X given the theta is directly is hard. So, for that is the reason why we are using EM. So, but calculating, so if you want to directly calculate the observed data from the model like maximum likelihood is difficult. So, what we normally do is we have a probability of x comma y given theta, where y is the hidden or missing data. So, if you use that y, the problem becomes simpler. Okay. So, the basic EM is you have complete data, which is the augmented data, X is the observed data or what is called as incomplete data, and Y is the hidden data, which is called as the missing data. So, example, if you have a coin toss problem, the observed can be the head tail sequences. So, you have a sequence of head and tail, maybe you take, we will take an example and see. Y is the hidden. The hidden could be which coin are you using. So, that could be coin ID sequences, and theta is the parameters that of the model. So, EM is an iterative method to perform maximal high likelihood estimation. So, basically we are still performing maximum likelihood estimation, but we are performing a maximized likelihood estimation to find the model given the data. So, starts with initial estimate for the theta and refines the current estimate iteratively to increase the likelihood of the observed data. So, that is what we are trying to do. So, let us take an example. The first example we are going to take is a coin toss example, and the coin toss example we will start off with in a simple case and then go along. So, the target is to figure out the probability of heads for 2 coins. You are given 2 coins, we want to find out what is the probability of heads. So, we want to make a maximum likelihood estimate. You can calculate this directly from the results, okay. And we will raise the bets a little higher, that is, will make a problem a little tougher, and assume that we do not even know which one of the coins is used for the sample set. So, what we do is initially we assume that we know that coin, and that information is known. So, we are not bothered about the coin. So, we just have to find out what is the probability of a sequence of head comings or a sequence of tail, head, tail, whatever. But in order to make this problem a little more interesting, what we do is we also assume that there is a probability in which the coin is chosen. We do not know that probability, okay, coin probability we do not know. So, this is the problem. This is the problem where we know the coin. So, let us assume we have 2 coins A and B. Here for understanding sake, we have colored it A as red and B as blue. So, here you have we will take some time to explain this this example, because the next we are going to go into the more interesting example. Here we have 2 coins A and B, okay, and the probabilities of heads are QA and QB. We are assuming that the first coin will be blue, the second coin will be green, the third coin red, the third will be red, the fourth is blue, and the fifth is red. Now, what we are doing here is we are having 5 sets of data. In each of the set we are tossing a coin 10 times, okay. So, the first one is the B coin, we are tossing the B coin 10 times and we are getting a head, tail, 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 head, head, tail, head, tail, head. So, that is what we are doing. So, the probability for the heads are given QA and QB, we know here. So, the probability of Q and QB is 0.8 and 0.45, we will see how this is done. So, the probabilities we want to calculate. So, 5 measurements are given, 5 measurement sets including the 10 tosses of each set are given, and we want to calculate the maximum likelihood probabilities. Now, here please note, we know which coin is tossed first, which coin is tossed second, which coin is tossed third. So, every time we get the values of the head and tails for each of the sets, we know that it is blue or red. That is why this is a simpler problem. So, how do we, even then how do we calculate the maximum likelihood? So, what we do is we first have the blue. So, blue coin when we toss, we got 5 heads and 5 tails. The second blue when we toss, we got 4 heads and 6 tails. So, altogether we have 9 heads and 11 tails. So, 9, we are only finding the probabilities of heads. So, QB, so for the blue one is equal to 9, the 9 heads divided by the total number 20, 9 plus 11, 20. So, 9 by 20, 0.45. So, QB, the probability of the heads coming out when you toss a blue coin is 0.45. Similarly, if you take the second set, the third set and the fifth set, all the 3 are red. So, I mean we know that a red coin is tossed, okay, and the total is 24 heads we get and 6 tails. So, 24 by 24 plus 6, that is 24 by 30, 0.8. So, the probability of heads coming when you toss when a red coin is tossed is 0.8. So, the idea here is you know that the coin you are tossing is red and blue. Remember that. What we have tried to do here is, depending upon the data given, 5 sets of 10 each, we are finding the maximum likelihood. So, this is the simple example. If this is there, what is EM there? There is no EM. So, what we are going to do to understand EM is, we are raising the stakes. Okay. So, we have calculated for this. So, what are we going to do? We are going to first assume that we have this, but please note, we do not know that it is a blue, a red, a blue and red. We just know that coins are tossed. Okay. So, the initialization we have to do. So, we do not know which of the coins is tossed in each set. So, you cannot calculate the maximum likelihood directly. In such a case, we have to use the EM. So, the situation where we have to use the EM is when we do not know which of the coins is tossed. This table here sort of seems to tell you that first is blue. No, we have just taken the example from there. So, now we at the first iteration during initialization, we are assuming this QA and QB is just an assumption. We are assuming that the probability of selecting a red coin, red is 0.6, and the probability of selecting the blue is 0.5. This is not calculated, this is just a guess. Okay. Now, what we will do is, as we do this EM algorithm, we will come to a convergence, and that final value is a ML estimate. So, what we are doing is, we are still calculating, as in the previous slide, we are still calculating the maximum likelihood only for QA and QB, probability of heads, but we do not know which coin is tossed. So, we cannot calculate directly. So, what we do is, we assume that we know, or I am sorry, we assume an initial value for QA and QB. So, that is 0.6 and 0.5. Now, we do not know which of the coins is tossed. So, we have to do the expectation step. Now, we will assume that the coin toss, that the number of heads and tails that come follows a binomial distribution. This is an assumption we are making. So, normally a coin toss follows a binomial when it is binary. So, we assume a binomial distribution. In this example, I will take only the first entries in this. So, what I do here is, the first step in the expectation. So, we are doing the second step, that is expectation, is we have to calculate the, we have to do some sample calculations. How do we do this calculation? We now we have cost in one step, we do not know whether it is blue or red, that we do not know, but we know that there are 10 sequences of coin tosses you do. Of course, we are assuming that once you take a coin, you will finish the 10, only then go to the next. That is an assumption we make. Out of which, from given this, we know that there are 5 heads and 5 tails. We yet do not know whether it is blue or green, that we do not. But we know that it has 5 heads and 5 tails. So, what we do is, we know that the probability of it being a red coin and a blue coin is 0.6 and 0.5. With those values, we calculate the 10, 5, the binomial values of 0.201 and 0.246. That is the first step. After we do that, we calculate the probability of you selecting a red or you selecting a blue. So, that is given by 0.45 and 0.55 by normalization, normalizing with the addition of the two values. So, from this we get the next table. This table tells me that in the first set, the chances of me choosing a red coin is 0.45 and a blue coin is 0.55. In the second set, the chances are 0.80 and 0.20. How did I arrive at that? We used, instead of 10, 5, we would have used 10, 9 and 10, 1. That is the number of reds and number of heads and number of tails I get. So, this way we got 0.45, 0.55 like that. Now, what is this giving you? This is giving you the probability that the first set is a red is 0.5, is a blue is 0.55. Previously, before we did this, we know that it is a blue. So, we know the probability. So, we knew it was 1 and it would have been 1 and 0, 1 and the second row it would have been, in the first one it would have been 0, 1 and so on. Now, it is not 0, 1 because we do not know which coin is chosen. So, that is the crux of the algorithm. So, we have finished this. After this step, so up to now we have still not finished, we are still in the expectation step. We have just calculated what is the we have not calculated the probability of head or all that. This is this table, the second table gives you the probability of choosing a red and a blue. Then after this comes the next step. Here what we have done is, based on this probability of 0.45, we are saying that, see, I have chosen in the first toss, I have chosen 5 heads and 5 blues. So, I will show you the how this is calculated. So, 5 into 0.45 if it is red is equal to 2.2 H, 5 again tail into 0.45 again 2.2. So, that is the calculation there, but I could have as well chosen a blue. Okay. So, it is 0.55 into 5 and 0.55 into 4, I am sorry, into 5, because 5. So, that gives me 2.8. So, I have 2.2 H and 2.2 tail, 2.8 H and 2.8 T. This is because the number of heads and the number of tails are 5 and 5 respectively. Okay. Like this I will fill it for all the 5 sets. So, now the acts that we did was, instead of assuming that I know that it is blue, I know it is red, we are actually doing a probability based on that. Once I do this, then the next step is the maximization, okay, or the M step as it is called. Now, in this M step what we will do is, we will use the values given here to recalculate QA and QB. So, this is the model parameters are recalculated. How did I do that? I know that the total is 21.3 H, 21.3 we are only doing heads. So, 21.3 plus 8.6, so 0.71 divided by, and QB is 0.58. So, if I had chosen the red, my chances of probability of heads is 0.71 and the probability of heads given the blue coin is 0.58. So, this is the first maximization step. Now, what do? We go back. Now, instead of using 0.6 and 0.5 which we did in the binomial distribution, we will now use 0.71 and 0.58. So, the probability of choice will be changed, that table will change. When that table changes, automatically my third table also will change. The first table we are just using it for the data, and so again my QA QB will change, and this goes on and goes on till between 2 iterations the probabilities do not change. When I complete in the 10th iteration, that is the convergence happens in the 10th iteration, we are not showing all the steps, and I get that the probability of head when I do a when I toss a red coin is 0.80 and when I toss a blue coin is 0.52. So, we started with 0.6, 0.5 as an estimate or guesstimate as it is called, and landed up with 0.80 and 0.52 as the maximum likelihood values. So, he has still calculated only the maximum likelihood values, and this is the flow of the EM algorithm for the coin toss example. Now, we will use this same EM method for k-means algorithm. Okay. So, the initialize the means. So, you have a mean mu k, and in the E step, the expectation step, you assign each point to a cluster depending upon this mu value. So, it could either belong to the cluster or not belong to the cluster. Now, in the M step what we do, given these are the clusters, we refine the mean mu k. So, we are assuming k clusters of each cluster k. So, what we do, you can actually randomly select any centers, some centers, then each point you assign it to the cluster depending upon how near it is to the center, and then given the new clusters re-estimate the value of the mu. So, this will stop when the change between the mu's is minimal. So, this is the step that we keep on doing. Okay. So, you go from this to this. Now, if there we just took a center, now assume that you are generating the data from a mixture of Gaussians. So, each instant x is generated by choosing one of the k Gaussians at random. There we just chose k means and generating an instance according to that Gaussian. So, just like we had how we chose the coin, here we can choose which of the k Gaussians we are going to choose, and the instance is generated according to that particular Gaussian. So, here we have shown 2 Gaussians. So, this is a Gaussian mixture. So, you have the pi, this is a you can see pi 1 equal to 0.7 and 0.2, and you have variance there, you have the mean and you have the mixing coefficient. So, you have a Gaussian distribution 1 and 2 Gaussian distributions like before, which have 2 different means, 2 different variances. Any Gaussian distribution has a mean and a variance, and you also have a mixture coefficient of 0.7 and 0.3. The total of the mixture coefficient should be equal to 1. So, what are we doing here? This Gaussian mixture is a very important concept used in complicated problems, but it is very simple to understand. We are taking x a value and we are saying that the probability, I mean the x can come from either the first distribution Gaussian distribution or the second Gaussian distribution in this mixing ratio. So, now let us try to connect k-means and mixture of Gaussians. K-means is a classifier and mixture of Gaussians is a probability model. So, we can use it to develop a soft classifier. So, we want to a parameter to fit the data mean, that is mu of k. So, the parameters to fit the data are the mean and the covariance and the mixing coefficient. These are the three parameters of the model. Now, we are talking about the model. The model in the initial case, in the simple case of k-means as a classifier, we used only the mean. Here we are going to use the mean, the covariance or variance and the mixing coefficient. So, here we have the known input and we have the classifier and we have the cluster parameters. So, this is just simply for k-means classifier and this is the classification results. We keep doing this till you converge. Now, so the cluster parameters will keep on being different depending upon the mean values. Now, you can use the EM algorithm for estimating k-means. So, given are instances from x generated from by a mixture of k Gaussians and you do not know the means of the Gaussians. So, of the k Gaussians you can, it is mu1 to mu k, we do not know the value. We do not know which instance of xi was generated by which Gaussian. This is almost similar, you can map it to the coin. We do not know which coin gave you the toss, I mean that sequence. So, we want to determine the maximum likely estimate of the means, that is what we want to do. And think of full description of each instance as y x zi1 and zi2. So, the zi1 is 1 if, so what we are using these sets to say whether it has come from the first which Gaussian. So, whether it is from j x is 1 if xi is generated by the jth Gaussian, like that we are doing, and xi is observable and xij we do not know where it is coming. So, it is unobservable. So, initialize the Gaussian parameter parameters mean mu k and the covariance and the mixing coefficient. You just initialize those values and the each step is you assign, no, so the initial is you are guessing, like how we guessed QA and QB in the coin toss. Here we are just assuming these are the Gaussians, you can't just do it very it is better to make an educated guess. So, in the each step, given the data value, you assign it to each of the Gaussians with a score for each cluster, not the Gaussian. You take now the each cluster is defined by a Gaussian distribution and that Gaussian distribution is the fitness of, I mean the assignment of a point to that particular cluster has an assignment score. Okay. Then the mth step. So, given the scores you re-estimate mu k, those three the parameters mu k, covariance, that is the mean, covariance and the mixing for each of the clusters k. Remember these three are the parameters. Now, the Gaussian mixture or the Gaussian is distributing a cluster instead of just a mean. So, you have the mean, the covariance and the mixing coefficient. So, for each of the clusters you redefine this given the scores. So, and then you likely evaluate the likelihood. If likelihood of parameters converge, you stop. So, basically given those scores you will adjust the values. With those values again you will calculate, then again you will give a score, then again you will calculate the model parameters, go back and so on. So, once you finish the model again you will calculate. So, essentially what we are doing is you are assigning each point xn an assignment score given this way and this score for each cluster or Gaussian k, that is now how much is this Gaussian k responsible for the point xn, that is what essentially what you are saying. So, this is calculated using the formula given below. This is a scoring formula, you could have used any scoring formula, but here we are using the mixture formula divided by the total. So, what we are doing is we are assuming that for this particular kth cluster the mixing parameter and the mu k and the psi k which you have guessed or you have got from the previous step, and then we are looking at that and then we are taking the summation of that and doing it. Okay. So, the m step for each of the Gaussian k, you will update the parameters with the new values. So, mu value will change now, covariance value will change and the mixing value will change. This is change. How does it change? You take the mean is the normal calculated mean, and nk is that total value of the score, and mixing coefficient you just say nk by n, and the covariance you take by old versus new and transform of that. So, that way you can find the covariance. So, these are the 3 new values you have got because of the score. So, that score is what is the important here. Okay. So, this is the total number of points that we are considering, and then you evaluate the log likelihood. If likelihood of parameters converge, stop, otherwise go back to the step. Okay. So, what are the strengths of EM? Numerical stability. In every iteration of the EM algorithm, it increases the likelihood of the observed data. So, that is the stability. It handles the parameter constraints quite gracefully, and the problems with EM is convergence can be very slow on some problem and is intimately related to the amount of missing information. The more the missing information, the more the time for convergence. The convergence it guarantees to improve the probability of the training data, has nothing to do with reducing the errors directly. It is just that the data you are trying to fit properly, that it tries to guarantee. It cannot guarantee to reach a global maximum. Sometimes you may get stuck with local maxima or saddle points, and the initial values are very important. If you give initial values wrong or we say random, then the convergence can be really slow. So, summary. We have explained the concept of expectation maximization using a very simple example of a coin toss, and then extended it to k-means using Gaussian mixtures. And we discussed using the coin toss example as already told, and then we outlined the use of EM for a realistic k-means algorithm example. So, thank you.